In this class, we study the electromagnetic waves in vacuum and monochromatic plane wave solution of electromagnetic wave. And we are familiar with Maxwell's equations. And first, we will write down the Maxwell's four equations, and from that equations, we will obtain the expression for electromagnetic wave, and then we derive we obtain the solution for wave equation. Electromagnetic waves in vacuum. Electromagnetic electromagnetic waves in vacuum. Electromagnetic waves in vacuum. So first we will write down the Maxwell's equations. Maxwell's equations. We have the Maxwell's equations as the first Maxwell equation as del dot E equal to rho by epsilon 0, where rho is the charge density, and E is electric field intensity. The second equation is del cross del dot B is equal to, second equation is del dot B is equal to 0. This is Gauss's first equation is Gauss's law in electrostatics, and the second equation is Gauss's law in magnetism. The significance of second equation is that the magnetic monopoles does not exist. If the magnetic monopole exists, then del dot B that should not be equal to 0. Since the magnetic poles are existing in dipoles, we will be always having del dot B as 0, which is Gauss's law in magnetism, and del dot E equal to rho by epsilon 0, which is obtained, which is the differential form of Gauss's law in electrostatics. The third equation is del cross E equal to minus dou B by dou T. B is a function of space and time coordinates. It's a function of x, y, z and t. So the differential is partial derivative, and the time derivative of B, that will be negative of that, will be equal to del cross C, which is obtained from Faraday's law. Faraday's law of electromagnetic induction, which is Faraday's law which is obtained from Faraday's law of electromagnetic induction. And the fourth Maxwell's equation is del cross B equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. Mu 0 J plus mu 0 epsilon 0 dou E by dou T. Del cross B equal to mu 0 J is differential form of Ampere's circuital theorem, and Maxwell modified the Ampere's circuital theorem. In addition to actual current, conduction current, Maxwell introduced a term called displacement current. The displacement current density, which is given by epsilon 0 dou E by dou T, and Maxwell introduced the concept of displacement current. So in addition to J, we are having one more current density called the displacement current density, and the equation, this equation is called modified Ampere's circuital theorem. This is modified Ampere's circuital theorem, and we are going to write the Maxwell's equations in vacuum or free space. free space there is no charge density, no current density. So in charge free, current free region, in charge free, current free region. So we are dealing with the free space where there is no charge and no current density. If rho equal to 0 and J equal to 0, then the case with the free space. In free space, if there is no charge and no current density, then we can write these equations. The Maxwell's equations can be written as, if rho equal to 0, J equal to 0, then the Maxwell's equation becomes, Maxwell's equations become, first equation is del dot E is equal to 0. So this is equation number 1, del dot E equal to 0. Second equation, no change, del dot B equal to 0. Equation number 2. Third equation is del cross E equal to minus dou B by dou T. No change in that equation. The fourth equation is del cross B is equal to, del cross B equal to mu 0, sorry, J is 0, so it is mu 0, epsilon 0, mu 0, epsilon 0, dou E by dou T. This I am taking it as equation number 4. So these are the four Maxwell's equations in the case of free space where there is no charge and no current. These equations are coupled equations where the electric and magnetic field vectors are connected together. These equations can be uncoupled by taking the curl of equation 3 and 4. First we take the curl of equation 3. Taking the curl of equation 3. When we take the curl of equation 3, left hand side it is del cross C is equal to, right hand side we are having del cross minus dou B by dou T. Del cross C. Del cross C is del of del dot E minus del dot del of E. Del dot del is del square. So it is del square E. Del cross E is del of del dot E minus del square E. What is del dot E? In charge free region, del dot E is 0 from equation 1. So this term is 0. So this will be minus del square E. So left hand side we are having minus del square E is equal to, right hand side we are having minus of del cross dou B by dou T. This del operator is space component dou x by dou x into x cap, dou by dou y cap plus dou by dou z cap. This space derivative and this one is time derivative. This x, y and z are independent coordinates. X, y, z and t are independent coordinates. If they are independent coordinates, then we can interchange the order of operation. First you are taking the time derivative, then you take the space, then operating with the space component, or first you operate with the space component, then take time derivative. Both are identical since this time and space components are coordinates are independent coordinates. So you can interchange the order of operation. First you take in here we are taking the time derivative. First we are taking time derivative, then we are taking curl. Instead of that you can take, first you can take the curl of B, then take the time derivative. So this del cross dou by dou T, I can replace it as dou by dou T of del cross B. Del cross and dou by dou T, that operations I am interchanging since the space coordinates and time coordinates are independent coordinates. So right hand side I am writing it as dou by dou T of del cross B. This negative sign will get cancelled. What is del cross B? Del cross B is mu 0 epsilon 0 dou E by dou T. So left hand side we are having del square E is equal to, right hand side we are having dou by dou T of mu 0 epsilon 0 dou E by dou T, or we are having del square E equal to mu 0 epsilon 0 dou square E by dot T square. So here we are having one equation for electric field vector del square E equal to mu 0 epsilon 0 dou square E by dot T square. This is equation number 5. So this is the expression for electric field vector. In a similar way, we can write the expression for magnetic field vector by taking the curl of equation 4. Take the curl of equation 4. Taking curl of equation 4. So del cross B is equal to right hand side. Del cross right hand side we are having del cross B equal to mu 0 epsilon 0 dou E by dot T. So this del cross B can be written as del of del dot B minus del dot del square B is equal to mu 0 epsilon 0. I am interchanging the operation del cross and dou by dot T. So I am writing dou by dot T of del cross C. So left hand side del dot B is 0. So this will be minus del square B equal to mu 0 epsilon 0 dou by dot T of what is del cross E. Del cross E is minus dou B by dot T, or we can write del square B equal to mu 0 epsilon 0 dou square B by dot T square. So this is equation number 6. See equations 5 and 6. They are identical to the wave equation in three-dimensional case. In three-dimensional case, we have the classical wave equation as in three dimension as del square f equal to 1 by v square into dou square f by dou t square. So these two equations are identical with the classical wave equation del square f equal to 1 by v square dou square f by dou t square. That means these electric field and magnetic field vectors, they are identical to the wave equations, and they are propagating with a speed. Comparing these equations, we can say that 1 by v square is equal to mu 0 epsilon 0, or I can write v equal to 1 by root of mu 0 epsilon 0. So the Maxwell derived the expression for electromagnetic wave in free space as 1 by root of mu 0 epsilon 0. In SI units, we have the value of mu 0 as 4 pi into 10 raised to minus 7 and epsilon 0 as 8.85 into 10 raised to minus 12. And by substituting this value in this equation, Maxwell obtained the velocity as approximately equal to 3 into 10 raised to 8 meter per second. Surprisingly, this velocity, which is found to be the velocity of light, which is experimentally determined much before the time of Maxwell. So this is velocity of light wave, which is experimentally determined earlier. So Maxwell showed that this is a surprising result. Maxwell derived the expression for velocity, and he found that all the electromagnetic waves are traveling with the same speed in free space, which is equal to the velocity of light. So light is an electromagnetic wave which is associated with the electric and magnetic field vectors. So this is the wave equation for an electromagnetic wave.